Hi guys, like I said last week, I wanted to actually be able to finish talking about pH and hydroxide as well as hydrogen ions and why that matters and how that relates to water. Due to some emergencies experienced by this little one, our recording comes a few days after I wanted it to, so she's on the mend, and let's get started here. Quickly going back to the learning objectives for Chapter 2, I just wanted to remind you right here that we're going to be looking at how water ionizes and what that means, and then how that relates to pH. We had left off a little bit past Section 2.4, Unique Properties of Water, and I just wanted to remind you that since water is a polar molecule, remember that Mickey Mouse head shape where it has 2 hydrogens and 1 oxygen? It is polar, which means it has a charge to it. In this case, water is slightly electronegative. Because of this, and here's a better picture of it, anything that is attracted to water and vice versa is called hydrophilic. And hydro refers to water and philos is loving. So you might think of other words that have philos in them, like philosophy. Philos is loving and Sophie is knowledge. So it's literally loving knowledge, which is kind of awesome. When molecules are polar, they can easily form hydrogen bonds. So how this relates to what we're going to be learning later on is this right here. This is a little picture of a cell membrane, and it's actually made of these little, what are called lipids. The heads, or these little spherical parts of the lipids, are attracted to water. They are hydrophilic. They love water. So that's why you find water outside the cell, as well as inside the cell, because there's these heads here. But in the middle of this cell membrane here, these phospholipid tails, we call them, they are hydrophobic. They do not like water. So a phobia is to be afraid of something. So literally they are afraid of water, and they do not form hydrogen bonds with water. Another look at that would be if you were to have some soap represented here in some water, and that soap surrounds or is hydrophobic with oil, for example. So if you're washing oil on your hands, this is literally why soap is able to remove that oil from your hands. On a similar note, we might relate this to how salt dissolves in water. So if you remember that lattice work, or the ionic bonds that hold Na and Cl together, that would be table salt. If you put that table salt in water, as long as you don't have so much salt that you're seeing a big clump at the bottom of your water, you will notice that the salt dissolves. So what does that mean when salt dissolves in water? If you look at the Na and the Cl right here and here, you can see that they're literally surrounded by these little Mickey Mouse heads, these little water molecules. Because this ion and this ion are polar, and so is water, so they like to be basically attracted to each other, and you're kind of obscuring the little NAs and CLs inside the water, which is chemically how you would show that the salt dissolves in the water. Here's another connection of how this relates to you. So Section 2.5 is the ionizing of water, and if you remember, an ion is just a charged particle. So if you look at water itself is held together covalently, but sometimes that bond breaks spontaneously or on its own. And what that looks like is this. So you recognize H2O as water. This arrow shows a reaction happening both to the right and to the left in an equilibrium. When water breaks apart into its 2 hydrogens and oxygen, when it ionizes, it actually looks something like this. It breaks apart into an oxygen and a hydrogen, as well as just a hydrogen ion. So we call the OH negative the hydroxide. It's negatively charged, and then a positively charged hydrogen. And there you go. And so why does this matter? Let's read on. This matters specifically in living organisms because pH, or the amount of hydrogen ions that you have in a solution or in your body, is really important in terms of homeostasis. So the amount of H+, or hydrogen ions from water, can be measured, and we call that measurement pH. pH is logarithmic, which means when you see a unit of 1, it's actually a 10-fold change in the amount of hydrogen ions in that solution. So here's a little kind of way to drive this home here. Pure water, or neutral pH, is right here at 7. So since this is a logarithmic scale, if you see 10 to the negative 7 power, that's actually how many hydrogen ions there are and how concentrated this solution is. So pure water is 7, or 7.0, neutral. So here's an example. You see the same amount of hydrogen ions as hydroxide ions. Now if you look at blood, blood is not quite 7, it's between 7 and 8 pH. Anytime you go towards the larger numbers on the pH scale, you're talking about something that's more basic or more alkaline. So blood is slightly alkaline, but that's where you want it for homeostasis. If you look at seawater, it's even a little bit more basic, but it needs to be that way, or it is that way, or I should say the living things that live in the water are that way because of this pH. And then you can see baking soda is a little bit more basic. Great Salt Lake is 10. And then you see some of your household cleaning products are quite basic or alkaline. When something is basic, there are less hydrogen ions in it and more hydroxide, conversely. So if you go towards the smaller numbers on the pH scale, you can see these things become more acidic. So if you look at pure water, 7, our urine and saliva is actually slightly acidic. Black coffee and rainwater is even more acidic. Tomatoes even more so. And then you've got things like pop and your stomach acid and hydrochloric acid, and battery acid is down here in these smaller numbers too. If you'd like to see this a little bit more written out, I'll show it to you like this. So pure water has neutral pH of 7. So that means there's the same amount of hydrogen ions and hydroxide ions, just pure water. But anything that dissociates or kind of comes apart in water increases the hydrogen ion concentration, and acidic substances have pH values below 7, which means between 0 and 6.9. And then conversely, bases or alkaline substances have more hydroxide ions than hydrogen ions. And I forgot to point out here that these brackets around this ion here, those indicate concentration. So for the most part, you'll notice that a lot of living things have pHs fairly close to 7. If there's a deviation from this, this can negatively impact that organism's metabolism. So to combat that, we have buffers, for an example, blood plasma, that release hydrogen ions and try to maintain that constant pH in our body. So here's an example. Normal pH is a little bit alkaline, a little bit basic. So you see between 7.35 and 7.45. Alkalosis, you remember that word I used before, alkaline? That's even more basic, so sad face. And then if you go the other direction, acidosis, that sounds like acid or those low pH numbers. And you're seeing very slight little differences here, but having big consequences. So even more than slightly acidic, death, and a little bit too basic, also death. I hope that was a pretty good overview of pH for you. I'd like to answer any questions that you have in class on Wednesday. And as just a reminder, you have the Chapter 2 guided questions and objectives to take a look at before we meet next, as well as the Chapter 2 Learn Smart. Alright, so with that, that is my final coverage of Chapter 2 for you. And you also have the, as a reminder, the Chapter 3 Learn Smart to take a look at, and I'm sorry, not the Chapter 2 Learn Smart, the Chapter 2 homework, prior to when we meet on Wednesday, September 7th, it should be. And then we'll be right back on track. We'll do Chapter 3, which are the macromolecules, on Wednesday together, and then we'll go from there. So I hope you guys are having a really good Labor Day weekend and enjoying friends, family, pets, all that good stuff, maybe sleeping, maybe having some good food. Alright, I will see you guys in class Wednesday, and please let me know if you have any and all questions, and I will be checking my email here and there today, as well as definitely tomorrow. Alright, thank you.